All right, polynomial functions of degree 2 are also known as quadratic functions. Um, and this is the form. If we have a function that can be eventually written in this form, then we have a polynomial function of degree 2, also known as a quadratic function. It is important to establish that a cannot be 0, because if a is 0, then the equation, let me write this down. If a was, so a was 0, then f becomes f of x equals, well, 0 x squared plus bx plus c, but then this simplifies down to just bx plus c. Well, the whole thing simplifies. And then we don't have a quadratic equation anymore. We have a linear equation. Um, so we have to establish that a cannot be 0 whenever we are talking about degree 2 polynomial. Very, very important. Also, be aware that if a polynomial starts out not being quadratic, but then eventually, if we can write it as a quadratic polynomial, then we have a quadratic polynomial. So let me give you an example of a disguised quadratic polynomial or quadratic function. So f of x, say, is, just to give a simple example, x minus 2 cubed. And then if we take away x cubed, some of us might be thinking, hey, there's an x cubed, so this is not quadratic. It would be cubic because of the exponent of 3, plus here we have another cubic, so this may look like cubic, but it isn't cubic. It is not cubic. This polynomial or this function is not cubic, and because when we fold this out, remember how we do that. X minus 2 times x minus 2 times x minus 2 minus x cubed. Now, I'm not going to go through every little step. Please, in your notebook, try to go through the steps of this. Um, we have multiplying those two give us x squared minus 4x minus 4. And then we still multiply by x minus 2 and take away x cubed. And then multiplying those two is a little more work, but we end up with x cubed minus, boy, 6x squared plus 12x minus 8, if I'm not mistaken. Double check that this is correct. I'm pretty sure it is correct, but now that is for the product. And then we still have to subtract x cubed. And then when we subtract the x cubes, we end up with negative 6x squared plus 12x minus 8. And that is, excuse me, and that is a quadratic function because there's the x squared. So this would be, will take the place of the a, this takes the place of the b, and this takes the place, of course, of the c, including the sign. So this c is negative 8, b is positive 12, only the 12, mind. So let me write this down to make it clear. So a would be negative 6, not negative 6x squared, just the negative 6. B is the coefficient of x, which would be 12x, rather, see, I said that wrong, just the 12. And C is negative 8. So no x's in A, B, C. Those are the coefficients of x squared, x, and, well, there's no x in there. So the point I wanted to make here, though, is that this function started out looking as if it wasn't a quadratic equation, but it is. There it is. It is a quadratic function, rather. Um, yeah. Sometimes we have, as an example, too, a quadratic function, such as x squared minus 7. Um, and that, of course, means that a would be 1, b, in this case, is 0, and c would be negative 7. So I'm just showing you what the a, b, and c respectively would be. Yeah. Um, so that is it. I was going to show you another example, but now I lost it. So every quadratic function, such as this one, is going to give us a parabola. Oh, before, maybe I do remember something here. Compare this with another example, example 3. F of x equals x minus 7 quantity squared. Do not confuse those two examples. Oh, I guess there is another one, 4, and then I'm going to come back to those two examples. F of x equals x squared. This is the simplest, absolutely simplest quadratic we can have. A is 1, B is 0, and C is 0. And that fulfills the requirement of a quadratic because we have this form where A is not 0. In this case, A is 1. The other two could be 0. That's okay. No problem with that. But A may never be 0. Okay. What I was going to tell you up here is please do not confuse this versus that. That is a shift down. If we start out with x squared, shift down, and this is a shift to the right. Shift down, shift to the right. And this is a regular parabola. Become familiar with what I would call a regular parabola. So it starts at 0, 0, then it goes up to 1, 1, and then 2, 4, and negative 1, 1, and negative 2, 4. And it has this kind of shape, a regular parabola, and it goes up in the same fashion. So on the right, it keeps going to the right. It's getting sharper. The way it increases gets sharper. So, you know, it may look like it's eventually going straight, but it never ever does. It goes towards the right. And there is no vertical asymptote. It keeps going always, always to the right. It will sweep rightwise, on and on, as it will continue going up. So there's no vertical asymptote. This guy is a shift to the right by 7 units. Before I continue, let me come back to this. The point down here is where it turns from one direction into the other direction. It's called the vertex. This line through its center, the center of the parabola, is called the axis of symmetry. Axis of symmetry. So we have to become familiar with parabolas. Oh, by the way, the shape is a parabola. And we have to become familiar with the parts of the parabola, such as the vertex, the axis of symmetry, x-intercepts, and y-intercepts. So there's only one intercept, which is both the x-intercept as well as the y-intercept, and that is 0, 0. So that is the intercepts. And the general shape, it opens up. There are parabolas that open down, opens up. So this one compared to this one is a shift to the right. So it will be 7 units to the right. The vertex will be at 7, 0. You know, there's not enough room for this guy. So let's go back to example 3 on, well, let's try to squeeze it in here. So this example is 7, 0. The equation of the, yeah, there's not enough room. Let's go back to example 3 on a new piece of paper, and that is f of x equals quantity x minus 7 squared. So this is example 3. And let's draw a nicer picture. Eventually, the graph will cross the y-axis. So what I do, because the graph will open out indefinitely. So what I do is actually draw the picture this way, looking at where it may cross the x-axis. And this picture is not going to be to scale. It is going to be a sketch. Please notice the difference between a sketch versus a graph, or a proper graph of the function. I'm going to mention this in future videos as well. A sketch is different than a graph because the sketch will not necessarily be proportionally correct, but it will give us all the information we need. So when we are drawing this by hand, we want sketches. We don't want a perfect graph. A calculator will give you a really, really perfect, well, close to a perfect graph. A graphing calculator will do that, but we don't want that. And I'm going to tell you why not in a moment. Perhaps with even more examples. So this sketch, the sketch is already wrong because the sketch shows that the graph is crossing the x-axis. And that is not true. This is a shift from a regular x squared function perfectly across horizontally to the right. So yes, this is not correct if we're looking at that. So, and the reason why is because I was paying too much of attention to the y-intercept, and then I didn't realize that the way it was supposed to go is this way. It touches the x-axis at one point. Yeah. So even though we want a sketch which is not necessarily to scale, the sketch has to be correct. It has to be accurate in the sense that if we're crossing the x-axis, then we have to show it, but the graph is not crossing the x-axis, so we do not show that at all. So this point is 7, 0, and then this shows the y-intercept. And we can figure that out. If x is 0, let's figure this out here. F of 0 would be quantity 0 minus 7, minus 7 squared, and that is quantity negative 7 squared, which is negative 7 times negative 7, and that is 49. So the y-intercept is 0, 49. The x-intercept is 7, 0, and we go through the origin. No, I'm sorry. We don't go through the origin. We go through the vertex, and this line, which has equation x equals 7, is the axis of symmetry. Axis of symmetry. Note that the vertex is the same as the x-intercept. So sometimes a point has double duty. So in this case, the x-intercept is the same thing as the vertex. It is both. Yeah. Not to be confused with example 2. So I'm backtracking a little bit because I want to elaborate on the examples. Example 2, f of x equals x squared minus 7. That is a shift down by 7. So remember our transformations of functions from a different video. We're shifting down by 7, our standard parabola, or our basic parabola. So we go down to 7, and the graph does that kind of thing. This point is 0, negative 7. That is the y-intercept as well as the vertex. So it is interesting here. This point is the x-intercept and the vertex, or the vertex is the x-intercept. The vertex is the y-intercept as well. It is both. Isn't that interesting? The x-intercepts are 2, so that is when that quantity is equal to 0. We can solve that equation very, very quickly here. X squared minus 7 equals 0, so that means x squared equals 7, and that means that x equals plus minus root 7. So the one on the right will be root 7 comma 0. The one on the left, the x-intercept on the left, will be negative root 7, 0. And so those are the important points on the graph. And we have also a axis of symmetry, which will be x equals 0. So there's a lot of information we have to draw from a quadratic function. The very first thing we have to pay attention to is the coefficient of x squared, what a is. By the way, in this case, did we say what it is in example 2 back here? Yeah, we said a is 1, b is 0, c is negative 7. Here, it isn't clear what a, b, and c is at first sight. That is interesting. It isn't clear what it is. Yeah, we have to FOIL this out to unpack a, b, and c, because this is not x squared with a number and then x with a number possibly. And no, this is not in general form. So this form of the function, we will call it general form of the quadratic function. So it's the general form if we have a x squared plus bx plus c. There's a couple different forms. So this is not, where was I? Here, this in example 2, this is not in general form. So we have to FOIL this out to figure out what a, b, and c are. So when we FOIL it, we get x squared minus 14x plus 49. So a is 1. That is the coefficient of x squared. B is negative 14. And c equals 49. I can see asking a multiple choice question on a test where I would be asking perhaps for A or B, even better. B, which one is it, negative 14 or negative 14x? And I can see some students thinking, oh, it's negative 14x. No. The B is just the negative 14 without the x, without the variable. So those are the coefficients of the polynomial. Yes. Yeah. So one reason why it is important to realize what the coefficients are is because here's a fact. If a is greater than 0, and we're talking about assuming that we have ax squared plus bx plus c, then the parabola opens up. So that kind of parabola. If, on the other hand, if a is less than 0, then the parabola opens down or downward, either way. So not that, the other way. And right now we're just going to look at two parabolas, either opening up or opening down. Yep. If a is not 0, rather, if a is equal to 0, not equal, because we have three choices: greater than 0, less than 0, or 0. If a is equal to 0, then we don't have a quadratic. Remember what we said earlier, we have to have that a is not equal to 0. Otherwise, we don't have a quadratic function. We have some other function, but not quadratic, perhaps linear. We don't know. We have to look at the function itself and see what it is. Okay. So if we have, as an example 5, f of x equals quantity x squared minus 7. Sorry, I was, let me just scratch that. Sorry about that. I was distracted for a moment. I meant to say x minus 7 quantity squared plus, I don't know, 8. Okay. Now remember our video about transformations of functions. This means that we are shifting to the right. The x squared is being shifted to the right by 7 units and then up by 8. So this setup gives us a lot of information right away. I know that the vertex will be 7, comma 8 without doing too much thinking. All right. So without doing computations, I know that the vertex will be at 7, 8, 7, 8, and the parabola will open upward this way. It will eventually cross the y-axis. So here I kind of force the cross. Sometimes what I do is just I draw the picture and then put the 7, 8 afterwards. That way I don't have to force. The pictures don't look more gracefully that way. By the way, they're not going to the crossing. The y-intercept is not 0, 8. It will be 0 blank, but where does it go? We don't know until we find f of 0. F of 0 will be, well, 0 minus 7 quantity squared plus 8, and that is 49 plus 8, 57. So 0, comma 57. And again, this is a sketch, not a graph, in the sense that, or a sketch of the graph, in the sense that it is not scaled well. Somebody could say, well, if this is 8, it doesn't make sense that this is 57. 8, if you double that, that is 16. And then if you add 8 more, that it would be about 24. So it doesn't make sense that this is 57. The picture is not scaled correctly. So this is what I called a sketch. This is a sketch, not a graph. But a sketch has to be well drawn. And what we mean by that is that we have to show the important parts, and the sketch has to be accurate in the sense that if the vertex is above the x-axis, we have to draw it above the x-axis. If the vertex is on the x-axis, we have to draw it accordingly. And if the vertex is below the x-axis, then we have to do that too. The scaling may be off, but not the accuracy of what is going on. Yeah. Yeah. We always, not always, but we many times need a good sketch rather than the graph, an accurate graph of anything, not necessarily just in mathematics. Most of us have seen that picture in science books where they have the sun and then the planets going in orbit around the sun, and then there is Earth somewhere, and then you've seen those kind of pictures, correct, where you have the planets and so forth. This picture, by the way, is not a scaled picture. This is completely, totally off. I mean, yeah. The relative distance of the planets to the sun compared to their diameters is nothing even close to this. If that was the case, we would be burned long time ago. If we were this close, this many Earths away from the sun, yeah. So this picture is really off. If we really wanted to draw an accurate picture, then we would have to draw the the planets as dots, and even so, I don't even know if that would be even accurate. But then we wouldn't be able to see what is going on. So this picture is wrong from a correct scale point of view. But we don't need a scaled picture to know what's going on. Um, So just be aware there is a sketch. So the picture we always see in books like this one about the planet system is a good sketch. It's not an accurate graph of or a picture of what's going on, because then again, the planets would be too small, the distances would have to be huge, and like a just to give you a comparison, pretend one planet was about the size of a baseball, and then the distance between planets would have to be somewhere in the neighborhood of football field lengths, like 100 yards, and then another planet, and then another 100 yards. So the picture is just not um, a real picture wouldn't be a good idea if we wanted to understand what's going on as far as the orbits. So the same thing is happening with the parabolas. We're not going to draw a very precise as far as scale goes. So we're going to give away the scale, but it will be accurate as far as where the points are. And that's why we have to label them. Oh, one thing I forgot to mention here is the axis of symmetry. So the axis of symmetry will be x equals 7. And we're always going to be asking you for all kinds of things, such as where's the y-intercept? Well, 0, 57. Where's the vertex? Well, 7, 8. Does it open up or down? Well, this doesn't show it necessarily, but when we FOIL it out, we're going to end up with x squared. And that means that the coefficient is 1. The coefficient of x squared is going to be 1, which is a positive number. So that means the parabola opens up. I don't mean to overwhelm you, but there's tons of information we have to draw from this function. So opening up, is there a y-intercept? Or what is the y-intercept? Well, there it is. Is there, or what is the x-intercept? Usually we're going to ask you for the x-intercept regardless. This one doesn't have any x-intercept, none whatsoever. It misses the x-axis completely. There's a huge gap. So when we ask for the x-intercepts, we simply say none. There is none, no x-intercepts. Now, the fact that the parabola opened up doesn't necessarily mean, rather, yeah, just because the parabola opens up, that doesn't mean there's no x-intercepts, because if the vertex is low enough, then we will cross the x-axis. If I was going to mention something else. If the parabola opens down, then if the vertex is below the x-axis, then there wouldn't be any x-intercepts. So pay close attention to the whole thing. 5. Example 6. More about scaling, because this will come back for future examples. So let's say we have x minus 7 quantity squared, and I'm going to exaggerate a little bit, plus 1,000. Wow. So it is the same kind of graph as this one, except that we're going to be 992 units above this, because if we already have the graph of this, and the only difference is that we're adding 992 because we already have 8. So 992 plus 8 is 1,000. That means that this graph is going to be shifted up by a, by a 992 units. I would probably graph it the same way. The only thing I would change is the numbers. So again, I'm emphasizing what the sketch versus the graph would be. So there you go, you got your parabola. So at this point, the vertex will not be 7, 8, as in the previous example. It would be 7, well, that was 49. No, it is 7, 1,000, because we are shifting to the right and up from 0, 0. And then the y-intercept would be 0, comma. If we plug in 0 here, we would end up with 49 plus 1,000, 1,049. Is this to scale? No way. It is not to scale whatsoever, because, come on, from here to here, there is 49 units, vertical units. And from here to here, there is 1,000. it doesn't make sense that this is 1,000 while this is 49 units. It just doesn't make sense. So that means the scale is messed up. The scale within the vertical axis is messed up. Still, I think this is a good sketch. Why? Because it tells us the main thing of everything that is going on. Sketches are good, a good thing, as long as we're aware we have a sketch. So this is a good sketch. The vertical axis would be x equals 7. All right. Now, if we already have the graph in this form or the equation in this form, the formula for this parabola in this form, we can right away tell where the vertex is, 7, 1,000. But oftentimes we're not given the formula this way. We're given the formula as x squared minus, in that particular case, minus 14x plus 1,049. So if somebody says, hey, here's the quadratic function, where is the vertex? Given this, given that, comma, what is or where is the vertex? Question mark. It's not obvious that it is 7, 1,000. We have to probably put the equation back into this form, and then we will be able to tell, oh, 7, 1,000. Because remember, this represents a horizontal shift to the right. And that is a little bit anti-intuitive. We did cover this in the video of transformations of functions. And this is a little anti-intuitive because to the right, you would expect plus 7, but no. X minus 7 means 7 units to the right. And then this one is correct in the sense that our intuition will be correct. If we put 1,000, that means 1,000 above 0. All right. So the process of going from here to there is what is called completing the square. So completing the square. And that's what we want to do. And this form is going to be called the standard form versus the general form. So this guy, again, is called the general form of the quadratic function versus the standard form. Yeah. So let's practice how to go from general to standard. And the reason why we want to do that is because once we have the standard form, it is very quick, it is very easy to obtain the vertex, which is very important. Example 7. So let's start with 7. We're going to practice how to go from the general form to the standard form. So let's say we have x squared minus 10x. That's it. Let's just leave it alone. And we want to know how to go from this form to the standard form. This is the general form to the standard form. We complete the square. So what we do is x squared minus 10x plus, how much are we going to add to complete the square? Hopefully we remember this. Divide by 2, so we got negative 10 over 2, which is going to give us 5, negative 5 squared. And so negative 5 quantity squared will be 25. Now, when we were doing circles, if we added 25 on one side of the equation, then we added 25 on the other side of the equation. But we don't want to change the function. We want to still have just the f of x on one side of the equation. So when we add the 25, what we have to do is subtract the 25 on the same side of the equation. And that does not change anything. We're adding and then subtracting in the same line. So we're really not changing the output of the function, the output is still going to be the same because we're adding and subtracting on the same side of the function. Okay, so this factors as x minus 5, remember, squared, and then we subtract 25. So that means that the graph is the vertex. So we're finished. This is, if we put down f of x, that is the standard form of this. So where's the vertex? Remember, this is a shift to the right by 5 units, and this is a shift down by 25 units. That is a little confusing because right and down and both are negative. So just be aware of that. So the vertex is going to be here. Which way does the parabola open? Up. Where is the vertex of symmetry? X equals 5, where the vertex is. What are the x and see? There's a lot of information we can draw from this one little function. So what is the y-intercept? Y-intercept. Well, we set 0 for x, and that is going to give us 0 squared minus 10 times 0, which is 0 minus 0. So the y-intercept point will be 0, 0. What about the x-intercept point? Well, that's going to be when we set the output to be 0, set 0 to be x squared minus 10x. So the output is 0, and then we solve for x. And you may say, well, isn't 0, 0 the y-intercept, the x-intercept as well? That would be 1, yes, but a parabola many times has 2 x-intercepts because it changes the direction. So we can factor this as x times x minus 10, and then we use the zero product property, which says that x equals 0, or x minus 10 is 0, and that means that x could be 10 or 0. So yes, the x-intercepts are going to be 0, 0, and 10, 0. Axis of symmetry is going to be x equals, the vertical line, x equals 5. So there's a lot of information. Which way does it open? Oh, it's already folded out. So what are the A, B, and C? Boy, there's a lot of information. A is 1, B is negative 10, C is 0. There is no constant. And you may be thinking, wait a minute, isn't that the constant? Oh, I can see that question. I can ask that question. You know, pretend if I give you this and I ask for A, B, C, you better not give C as negative 25, because the C corresponds to the general form, not to the standard form of the formula for the quadratic function. So there's a lot of stuff going on with parabolas. Parabolas are very rich in the kind of information they can give us. We can analyze parabolas for a long, long time. Yeah, and then we have the sketch. But I didn't want to focus too much on all this information. I wanted to focus from here to here. The rest is additional information we are gathering. Okay. Example 8. Okay, so I like to change one thing at a time. So example 6 was x squared minus 10x. I kept the minus 10x, but I changed the negative. In that case, we factor out the negative. The parabola opens down, but when we are dealing with the shift left or right, we have to keep the shift left or right separate from the opening down. So what we do is factor out the negative, and we have x squared plus 10x, because the negative gets factored out of the negative 10 as well. Okay, this is tricky, guys. So you gotta pay close attention. How much do we add to complete the square. 25 as before. Whoops, I missed the 2. 25. All right. So you may be thinking, oh, subtract 25 and we are set. Kind of. Yes, we're going to subtract, but this 25, as written in this bracket, is being multiplied by negative or negative 1. So yes, we're going to subtract the 25 multiplied with a negative. So minus negative 25. That is tricky. So whenever we're adding a number in a bracket, remember the bracket is perhaps been multiplied with something else, and that something else has to be taken into account. So we have minus quantity x. That's interesting because now we are not going to have minus 5 quantity squared. We're going to have plus 5 because of this positive quantity squared, and then double negative plus 25. So this will be the standard form of that guy. We still have the question. All right, what is the vertex? Vertex at negative 5, because now we're shifting to the left, comma, and then up 25. The parabola opens down. Does it open up or does it open down? That should be an easy thing to answer, I hope. What about the y-intercept? Well, if we plug in 0 here, then we got 0 and 0, and then we add the 0, so we get 0, 0. What about the x-intercept? You may be thinking, oh, well, it's the same as the previous one. No, 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 no. We have to so for the x-intercept, we set 0 to be the output, not the input, but the output to be 0. So we have 0 equals negative x squared minus 10x, and we can factor out an x. So we have x times negative x minus 10. And using the zero product property, that means that x equals 0 or negative x minus 10 equals 0. But be careful with this guy. That's not, you can easily trip. Anybody can easily trip on this. So move the 10 over, and we end up with positive 10. But then we got to multiply by negative 1 to get rid of this negative. Or you can multiply by negative 1 at once. Or you could divide this equation by negative 1 at the outset of the equation. It doesn't matter which way. There's a few different ways to get to the answer. Just make sure it is correct. So the answer is going to be negative 10. Yeah. Yeah, I was double checking because negative 10 plugged back into here is going to give us negative 10, but then another negative outside of that is going to be positive 10 minus 10 equals 0. So the x-intercepts are going to be 0, 0. So this guy has a double duty. It is 0, 0 is the y-intercept as well as the x-intercept. And the other x-intercept is negative 10, 0. I better use the word roll. This point has 2 rolls. The y-intercept and the x, it is also an x-intercept. I think that sounds better. Anyway, opening up, rather opening down, vertex. Oh, something I'm going to ask you to is the range of the function. See, the parabolas are very rich. They have a lot of information in them. So the parabola opens down. X-intercepts are negative 10 and 0. So this is a sketch of the parabola going through 0, 0, negative 10, 0. The vertex up here is going to be negative 5, comma 25. Yep. So that's a good sketch. And then we have the axis of symmetry, axis of symmetry, x equals 5. There it is. And then, oh, the range, boy, range. So the range is how far it goes down or up to, you know, if we, this arrows indicate the parabola keeps going down forever. So there is no bottom. It keeps going up, 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 up to this maximum point. So this maximum point tells us how far the output, and the output goes up to 25. Remember, the first coordinate has to do with the input. The second coordinate has to do with the output. So the most the function can yield as an output is 25. So the range is from negative infinity up to 25. And also this graph has a maximum point, a local maximum, which is going to be negative 5, 25. So we have, it's also a global maximum. But anyway, we have a maximum value of 25 when x equals negative 5. Or a maximum value of maximum at negative 5 comma 25. Yeah. So there's a lot of information we can draw from parabolas, and that's how the game works. How this is not a game, it's a class, but that's how it works. We have to be able to draw a lot of information just from this little equation. That's all we're given. Notice how much stuff we're getting to know about this graph. Okay, another example. 9. F of x equals, let's put a 5, x squared minus 10x. So I'm leaving this the same kind of function as example 8, 7, 8, yep, example 7, x squared minus 10x, except that we're now putting a 5 in front. In example 8, we have a negative in front of the x squared, but we still have the same negative 10x, negative 10x. Okay, so what do we do with this? Factor the 5. Just like in example 8, we factor the negative x squared, rather the negative 1, or just the negative, factor the 5. So why? Here's the thing. X squared, when we factor the 5, we also factor 5 out of this guy, minus 2x. Close the parentheses, leave some room to complete the square, and then we're going to subtract whatever we add into here. That's not quite totally correct, but okay. So this is the thing. Before we complete the square, we have to have a nice pure coefficient of 1. Okay, we must have I'm going to exaggerate a little bit, pure 1 as coefficient of x squared before we complete square. We have to have it. If we don't, then whatever we complete here is not gonna work. Things are not gonna factor out well. Yeah, it's just not gonna work. A lot of people want to know things. No. The way I want to say it is different. Sometimes we think there is a very, very high reason why something is the way it is supposed to be. Sometimes we think, oh, there must be some deep meaning behind something we do. And in my experience, in my personal experience, many of the things we do are just practical. We do them because they work. That's it. There's no deep meaning behind, many of the things we do. They just work well. So the reason why can we do this problem without factoring the 5? The answer is, yeah, we could. it is just more work. It is just unnecessarily more difficult than if we just factor the 5. I mean, yeah, just factor the 5 and things will work best. How much are we going to add? 1, because half of -2 is -1. Square that, and that gives us 1. Now, remember what we did in the previous example. Are we going to subtract 1? Yes, except that this 1 is being multiplied with a 5. See, it's being multiplied with a 5. So we're going to subtract 1 times 5, which is 5. Even though we added 1, in reality, we're not adding 1. We're adding 1 times 5. All right. So f of x can be written as 5 times, factor this, x minus 1, quantity squared, minus 5. That is a little confusing. This 5 and that 5. We got two 5s. Where's the vertex? Vertex is at 1, -5. This 5 does not affect the vertex once we have this written this way. Where is see, there's tons of questions. I'm almost overwhelmed in my mind as the number of questions we can ask. Does the parabola open up or down? Well, the coefficient is positive. A is 5. B is -10. C, if I ask for C, don't tell me there isn't. It is 0. It's just we never write down +0 as a final solution. So the vertex is 1, -5. The parabola opens up. Where is the axis of symmetry? Well, it is going to be at 1, x equals 1, which is a vertical line. What is the y-intercept? Well, that's when x is equal to 0. So plug in 0. Oh, we get 0, 0, 0. What about the x-intercepts? Intercepts, remember how we do that? Put 0, or set this equal to 0. So the other way, put the 0 here. Factor that. If we cannot factor, then use the quadratic formula. And then I'm thinking, well, let's just do it. There's a little bit of work here involved. So 0 equals 5x squared minus 10x. Factor as much as you can. So 5x, and then 5x. So there's still another x minus 2. So either 5x equals 0 or x minus 2 is equal to 0. But of course, we divide by 5. Or you could have divided by 5 here or here, either way. So x equals 0 and x equals 2. So the x-intercepts are 0, 0. So 0, 0 has two roles. It is the y-intercept and the x-intercept, but there is another x-intercept, 2, 0, 2, 0. Because the parabola opens up, we have a minimum. Yeah, we have a minimum, and the minimum is at the vertex, 1, -5. So let's sketch this. There we go. 0, 0 is an x as well as a y-intercept. And then we have 2, 0. And then we have here -1, rather 1, -5. See, right there, I can tell this is not to scale because this is 5, but this is 2. It doesn't even make sense. The 5 is smaller than the 2, but that's okay because this is a sketch. By the way, somebody could ask, well, so what is this 5 doing? What is the role of this 5? We know what this -5 does. It brings the vertex down here. But what about the 5? This 5? Well, if we were drawing this to scale correctly, if this was 2, then think about that. 2, 4, 5 would be here. So this would be much steeper, may look much, much steeper, which causes this to look more narrow. And that's what it does. The 5, that's what the 5 does. Stretches the graph vertically, a vertical stretch, which makes the graph look more narrow. It isn't that the graph is narrow, it is that the stretch makes it look more narrow. So that's how it goes. Yeah. Typically, with a sketch, we don't draw the vertical change because the sketch is supposed to give us a nice graph, and the stretch or the shrink, if there was a shrink, would cause the graph to deform, not to look as nice. We have to be aware of it, but we don't have to draw it in a sketch necessarily. So there's the axis of symmetry. The range, it goes from the bottom, which is -5, and it doesn't end. So the range goes from, this is a -5, a square bracket, to infinity. And the minimum, there's no maximum because parabolas that open up don't have maximums. This keeps going up and up forever. The minimum point so there's the minimum is -5 at 1. That's many times how we write the minimum. The minimum is the output. It happens when the input is 1. Okay. Let's look at a sort of weird example. Or it's not weird, it's just more complicated. So example 10. Let's say f of x is equal to 2x squared minus 3x plus 4. Okay, so I'm changing gears altogether. The previous example always had, well, the last few examples have a -10 and then no constant. This one is different. This one is more complicated. So the first thing we do is factor out the 2 in this case. So f of x is equal to 2x squared. Okay, here's one complication. But the 3 doesn't have a 2 embedded in it. We cannot really, it wasn't like a 6. If we had a 6, we can factor out the 2, and then we will still have a 3. Or if we had a 20, for instance, we can factor out the 2 and end up with a 10. So how do we factor 2 out of the 3? Boy, divide by 2. 3 over 2x. So that's one complication. We did not have this kind of problem before. How do we know this is correct before we start panicking? Oh my goodness, how do I do this? No, 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 no. Don't panic. I mean, panic, but a little bit. If we multiply back by the 2, the 2's cancel, and we still have the 3. So that's how we know we are correct. If we're in doubt, think about what should this be? So multiplied with the whatever we factor out gives us back what we started with. So we can say, oh, if we multiply by 2, the 2's will cancel, and then we end up with -3, which is what we started with. And of course, here there's no problem. 2 times x squared equals to x squared. Leave enough room for completing the square and keep the 4 out. A mistake some students make when they're doing this is they factor the 2 out of everything. No, 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 no. Keep your constant out of the way. Don't mess with it as far as factoring. Very, very important. Okay. We're going to complete the square here. How much do we need? That's another complication. Take the -3/2 and divide it by 2. Okay, so I'm going to do that over here. -3 over 2. And then we're going to divide by 2. So we're going to end up with a smaller fraction. We obtain a smaller fraction when the denominator is larger. I'm erasing the ink that I have in my hand, but somehow the pen, many times I grab it like this and then the ink ends up in my hand. So I got to wash it later. Anyway, um, it's not a tattoo. Some of you may be thinking, hey, that he has a tattoo on his hand. No, 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 no. Nothing wrong with that. I just don't have one. Um, so divide by 2, and which means multiply by the reciprocal. So let's do the steps. -3/2 multiply by a half, and that's going to give us -3/4. -3/4. Square that, um, and then add it into here. So that's going to be, boy, this is a complicated problem. 9/16. 9/16. And that will complete the square. Then we have to subtract 9/16. And some of you are saying, but wait a minute, isn't that 9/16 multiplied with 2? You are right, multiply by 2. Because we're not really adding 9/16, we're adding 18/16 when we multiply by 2. So I'm just going to write it times 2, indicating we're going to end up with 18/16, or we can just simplify the 16 and the 2. So this part was already a complication. Factoring the 2 could have caused an issue because, remember, we don't factor the 2 or whatever we need to factor out of the constant. All right, so we got the 4 still there. We're going to do this computation, and we're going to do this factoring equals to quantity x minus whatever the number was before we square it. So 3/4. Quantity squared. And then we got to do this guy. Now, simplifying that is going to give us 9/8. The 2 and the 16 simplify. So change that 4 into 8 plus 32/8, because 32 divided by 8 is 4. But then we have to subtract 9/8. So the 9/8 comes from here. And then the 4 became 32/8 equals to quantity x minus 3/4 squared. 32 minus 9, well, 32 minus 10, I know how much that is. That's 22. So since we're taking away a little less than 10, 23 plus 23/8. And there it is. It is the same kind of problem as before. It's a nice parabola. The shift is to the right and up. The difference is that we just have fractions, some weird fractions. See, and that's why I don't dwell too much on having a perfect graph. I mean, if I wanted a close to a perfect graph, I would just pull out a graphing calculator or do it on a computer. But we want to have an idea of how to obtain information from this algebraically. So I'm not against technology. We have to learn what's going on here. So we have a shift to the right and a shift up, mind, a shift up. And we have a parabola that opens up. So the vertex is to the right and up. We have something like this. The vertex has to be lower than the y-intercept. So the vertex will be at 3/4 comma 23/8. The y-intercept, and perhaps my parabola should have been a little longer, it should dip a little more, but it is a sketch. Now, the easiest way to find the y-intercept is to plug in 0 into the general form, because that's going to become 0 when x is 0. That's going to become 0. So this constant term is the output of putting 0 in the input. So this is going to be 0, 4. And then I'm not going to draw the rest of the information. We did this in previous examples. I just want to show you a sketch, a quick sketch. because the importance of this problem is how complicated the computations can be. There is an alternative to finding the vertex. You don't have to put the equation into standard form. We will have to put the function in standard form. Can we bypass the standard form? So that is a question here. So can we bypass the standard form? And the answer is yes. We memorize that the x, the input of the vertex is negative b over 2a. So that is the input of the vertex. It's always going to be that whenever we have a quadratic function. So as an example, I should have put the example number after, because this is not really the example. This is just a fact. So let's say f of x equals negative x squared minus 2x plus 7. And you want to know where the vertex is without having to complete the square. Can we do that? No problem. Piece of cake, actually, as long as you remember this. So let's just write down negative b over 2a. Oh, we need to establish what a, b, and c are, although c is not in this formula, but a, how much is a? Negative 1. B is negative 2x. No, it's not negative 2x. I was just checking to see if you were paying attention. And then C is 7. Okay, negative. B is negative 2. Watch out. Negative on the B over 2 times, whoa, this is confusing. 2 times negative 1. So there's a whole bunch of negatives going on here. Negative, negative, negative. 3. See how the ink keeps spreading? All right. Negative, oh, 3 negatives. So the output is going to be negative of this expression, the output of this expression. And then the 2's cancel. So we end up with negative 1. What is that negative 1? Well, that is the input of the vertex. So if we were to put this in standard form, we would have negative quantity because of that negative, and then x plus 1. That means that we have a shift to the left. Boy, that is even more confusing because that's where the vertex is. The x value of the vertex is negative 1, which is to the left. But that means that we have to put a x plus 1 on the equation. That is a little confusing. So I usually, I shouldn't say usually, but oftentimes I don't use this. I just go through the process of completing the square. But if you want to, you can use that. If we're not asking necessarily for the standard form, and you just want to know where the vertex is, well, that's the starting point, because you only get the input. You still have to figure out the output, or we have to figure out the output. Now, f of negative 1 is negative quantity negative 1 squared minus 2 times, I'm plugging negative 1 into this formula. Negative 1, so we have negative of negative 1 squared minus negative 2, or minus 2 rather, minus 2 times negative 1, and then plus 7. Negative 1 squared is 1 with a negative, or the other way to think of this is we got 2 negatives and an extra negative, 3 negatives, which is negative 1, 2 negatives, plus 2, plus 7. So that is a nice 8. So the vertex is at negative 1, 8. Okay, and if we were going to put this in standard form, I would know what to do here, 8, and then we're set. So you could cheat in quotation marks, and put this in standard form, bypassing the completing the square. If you do it right, yeah, if you do it right, you could bypass and get the vertex. That's the easy part, and then put it into standard form without actually having to complete the square. Now, the nice thing about that is that if you're in doubt, you can always expand this, fold it out, putting it back together, and it should look like that. Yep. Now, parabolas have many applications, tons and tons and tons and tons of applications. Yeah, many applications. I don't even want to start writing some of the applications, but I want to show you two applications too. I mean, if you every time you throw a projectile, the projectile will follow a parabolic trajectory. So even if you just throw a pen, well, you don't see it because the camera is above, but the parabola, the pen took parabolic trajectory. That is well established. It doesn't matter what projectile you use, we will have a parabolic trajectory because of gravity pulling it down. So that is just one application. We're not going to do such an application. We are going to do this application. This is a pretty standard application in many places. So let's say a farmer has 6,000 feet of fencing. Yep. And wants to fence a region or fence, yeah, an area, a rectangular area with, because if you try to do just a rectangular area and that's it, the best one that works as far as maximizing the area is going to be a square. A square is the optimum, but there's a twist to the standard problem in this. With fence through the center. So the question is, what is the best way to optimize area? Question mark. Okay, so let me draw you a picture. So a farmer has 6,000 feet of fencing and wants to set up a rectangle. Now, if it was just a rectangle, the answer is clear. It is going to be a square to maximize the area, and that has been established pretty well. You can do the problem on the side if you want to. It's a different problem, a much easier problem than this one. So if it was just a rectangle, the best one to maximize the area would be a rectangle that it would be a fourth of that per side, so 1,500 each side, and that will do. But we want an extra division in the middle, and we want to use 6,000 feet to do that. Which one is the one that is going to work the best? And that is not as obvious. So perhaps, yeah, this is not going to be easy. Let's say you do 6, and we don't know whether the optimum, the best way to do this is going to look like that, or whether, I'm going to exaggerate a little bit, we're going to have this shape. We don't know which one. Is this, long? So this division goes on the long side of the rectangle, or short? If we have a square, okay, let's pretend, let's say we are a little naive and thinking, oh, well, the answer has to be a square. So then we would have 5 sides, 1, 2, 3, 4, and then 5, or 1, 2, 3, 4, and 5. So if the answer was still a square, which isn't, I think it isn't, but we can check now. We will do that now. Then what would be each one of the sides? Well, if it was a square still, divide 6,000 by 5. Yep, because we have 5 sides, 1, 2, 3, 4, and then 5 sides. So each one would have to be 1,200. So 1,200 this way, and then 1,200 that way. And what is the area of this? The area would be base times height, but the base is 1,200. So base times height, and that would be 1,200 by 1,200, and that is 1,000. Well, it's 140. 12 times 12, I know, is 144. 144, and then we got 2 zeros here and 2 zeros there. 1, 2, 3. 1, 2, 3. So we have 1,440,000 square feet of area. And we may be thinking, well, that's a lot of area. Isn't that going to satisfy? Is it, the farmer? Isn't that the best? Well, pretend the farmer has tons and tons of land. So if they could find a way to do it even larger as far as the area goes, then we should go for that one. And doing it this way, sticking with the square, is going to give us 1,440,000 square feet. The challenge is this: can we come up with something, some kind of setup using only 6,000 feet, of fencing that is going to give us more area? All right, so let me draw the picture again. And we have to decide which one is going to be X, our independent variable. Some people would say, can we pick this to be X? The answer is yes. Some people would say, can I pick that to be X? And the answer is yes. But then we have to set it up differently. So let X be, and I'm just going to point to it, this side. Okay. So then the question is, what is that? If this is X, a generic X, then what is this? Well, we got 6,000. This is going to be fence all the way around, fence, and in the middle. So we got 6,000 to start with. If we label this as X, then we're going to use up X and X and X. So we're going to use 3 X's from the 6,000. So this is how much is going to be left over after using X, X, X. And then we have to use what is left over into 2 sides. So the other 2 sides are going to be 6,000 minus 3x over 2. That's this side. And all of it. Okay, so first we establish how we're going to label things. And by the way, I'm going to do the other way, pretending that this was X. How would the problem look like? We will do that after we finish this. Okay, so what do we want to optimize? That is very important. We have to think what we want to optimize. And we want to optimize the area, which is a function of X. If this is very short, this is going to be very wide, and we're going to end up with some kind of area. But if this is very tall, this is going to be narrow, and we may end up with a different kind of area. So the area is going to be base times height. And the way this looks is this is the base, this is the height. So the base is this. 6,000 minus 3x divided by 2 times times what? Oh, times the height, which is x. All right. So this is going to be 6,000x minus 3x squared, because we're going to multiply it through over 2, which is, now we're going to divide 3,000x minus 3 over 2 x squared. Some of you may be thinking, well, isn't that 1.5? Yeah, and it is true. In algebra, however, we prefer to keep the fractions. And then, because this is a quadratic, we typically put the quadratic term first. Negative 3 over 2 x squared plus, well, I put 6, and it should be 3,000. 3,000 in x. Now, we don't want the vertex or the, we don't want the vertex. No, I lied. We do want the vertex. What I meant to say is we don't want the y-intercept or the x-intercept. So that means we don't want to have 0 for x, and we don't want to put this equal to 0. That can be misleading. What we want to know is what the maximum is. This is a parabola that opens down. So it does this. And we're going to find the maximum area. This represents the area. We want to know what x value causes the area to be maximum. So we want the vertex. But in just a couple minutes ago, we realized that the vertex can be found very quickly without completing the square. We don't have to complete the square in this case, with the formula negative b over 2a. Or you can complete this, the square and get the vertex that way. But let's do it this way. So this is b. Let me write here on the side what a and b are. A is negative 3/2. B is 3,000. And c is equal to 0. Even though we're not going to use c, it's not a bad idea to still write it down. So opposite of 3,000 over 2 times a, negative 3 over 2. The 2's cancel, so we're going to end up dividing by 3, and the 2 negatives also cancel out. So we end up with 1,000. So the x value, which is going to maximize the area, is 1,000. Okay, so that means that this should be 1,000 feet. And then to figure out the other side, well, let's do that. So if x is 1,000, 6,000 minus 3,000 is 3,000. Divide by 2, this side has to be 1,500 feet. And by the way, when we multiply those two, that's an easy multiplication because this is a 1 and 15. So the maximum, I should have put it here, but it doesn't fit. So I'm going to put it on the side here. The maximum area is 1,500 times 1,000. It is 1,500,000 square feet, which is more than what we had perhaps guessed earlier. Remember, if we set this to be 1,200 by 1,200, we end up with 1,440,000 square feet. But if there is no limitations here, you know, if we have all the space we ever want, all the land we ever want to use, then if we make it 1,000 by 1,500, we're going to end up with 1,500,000 square feet. So we're going to have more square feet. We're going to have 60,000 square feet more than if we went this way. And that is the power of knowledge. Knowledge can be a good thing. Oh, before I forget, let me just write down the setup, because I don't want to box you into doing things just one way. There's many ways to do this. Well, at least two. Okay, so let's just, I'm not going to solve the whole thing. I'm going to let you solve it, but let's set it up differently. What if somebody says, hey, I want to label this as X, all of this X. How would I set it up? Okay, so if we start, by the way we did it just a little bit ago was by letting this guy be X, and then this guy was going to be 6,000 minus 3X divided by 2. And then we went through this, optimized, and found what X is and what the output should be. Okay. What if we have this as X? Then this side would have to be, let's see. Well, we start out with 6,000 feet of fencing. If this is X and this is X, we're going to take away 2 of those from the 6,000. Okay, so that's 2. And then what is left over, which is this quantity, has to be divided into 3. There we go. So the area, which is still a function of X, but the X is not the side, that will be the top and the bottom, will be base times height. This is the base, rather, this is the base, which is the same as that. X times the height, 6,000 minus 2X over 3. So that is 6,000X minus 2X squared over 3. And that is divided by 3, 2,000X minus 2/3 X squared. See, that's why I don't like to use decimals, because if somebody put this down, use this setup, they would end up with 2/3, which is 0.66666666666, you know. And if you round it and you keep the rounding, then we're going to be off by a little bit, which is going to count against us. So that's better not to use. It is better not to use decimals unless we have to, at least not in algebra. Now, in engineering and chemistry and other subjects, you know, we talk about significant digits and all that, and yes, then we would have to. So that varies from discipline to discipline. But anyway, let's rewrite this as negative 2 over 3x squared plus 2,000x, and we want to find the vertex because that is the place where we have the maximum. The parabola is not the same, by the way. This is not the same parabola as the one we just did. And let me finish this up. Negative b over 2a will be negative 2,000. And you're thinking, boy, that's not what we got. We got negative 3,000 here. You know, so doesn't seem to be consistent, over 2 times negative 2/3. And here things don't cancel as nicely as before. That's okay. That is, so let's cancel the 2 negatives first. So we got 2,000, and we're going to divide by, multiply this out, so we end up with 4/3. So we're dividing by 4/3. Remember, that is the same thing as 2,000 multiplied by the reciprocal. So 2,000 times 3 is 6,000. But then we divide by 4, and that is 1,500. And you may be thinking, wait a minute, isn't the answer x equals 1,000? That's what we got here, 1,000. Well, it depends how you set it up. We got 1500, but for x, but x is the top. So that is consistent with the other setup where the top is 1500. And then if we put 1500 here, multiplied by 2, that's going to be 3000. 6,000 minus 3,000 is 3,000. Divide by 3, we end up with 1,000. So we end up with the same answer, 1,500 feet across this way, and then 1,000 feet the other way. So it doesn't matter how we set it up. The answer is going to be consistent. We just have to know what's going on. So be aware, there's more than one way to do that. Let's do a second problem that is another classic of optimization. Okay, pretend you have this sheet, and I want to fold it this way. Boy, I'm getting ink all over. That's all right. That's an easy problem to fix. All I have to do is wash my hands. So I want this side to be the same as that. Okay, so there it is. That creates a sort of a container here. There's a volume here. And the cross section of this, you know, the camera only goes so far, so it will be this much. That's the cross section of it. Now, you can make this shorter, this area shorter. So it would be wider and short, or you can make it taller, you know, really tall. And pretend you're folding. Boy, this is getting, this looks a lot better if I had more. So this would be really, really tall. And again, the cross section, whoa, it's really close to the camera. Looks like this. Anyway, so here's the problem. What problem number is it? 12, yep, 13. That's one of my favorite numbers. 13. Okay, so you have a sheet of anything. It doesn't have to be paper, it can be metal. And we want to fold a distance so that we end up with this kind of thing. Well, I should have gone farther. There you go. There. So the question is, what folding, pretend this is a foot. 1 foot wide. And it doesn't matter how long it is. We don't want to necessarily know. So the question is, what folding will cause this area, the cross area, to be the biggest? So we want to optimize area. I think I put B when I spelled out optimize before. And those of us who are thinking, wait a minute. No, optimize. Yeah, I spell it right. Right. Some people will say, wait a minute, this is a math class, not an English class. It doesn't matter. We have to spell well. Oh yeah, I did put B. I don't know why. Yeah, it should be optimize. There we go. Not optimize. Optimize. Anyway, so we want to optimize the area. We want to make it optimize. Now, boy, optimize or optimize. Now I'm confusing myself. So please double check that. I don't know. I'll check. Anyway, optimize. Doesn't sound right. I think it's a B. Anyway, sorry to take time away from you. That's embarrassing. And we want to optimize the area. What is the maximum area we can have in here? And again, I'm not making an excuse. I have to go back and double check. We have to spell well, regardless of what class we are. That's it. So I'm not making excuses. It's wrong to misspell. Optimize. It's a P, isn't it? Anyway, I don't mean to be obsessed over that, obsessing myself over that. Anyway, what is the largest area? Yeah, let's just click change. Find the way to obtain largest area. So how am I going to fold it? And it has to be the same length. So the area is maximum. Okay, so for instance, let's say we have, by the way, 1 foot is the same thing as 12 inches. Okay, so just to give a couple of examples, if we fold up 1 inch on each side, 1 and 1, okay, across we're going to end up with 10 inches because you fold 1 on each side. You start with 12 inches. So the area, the cross area here, is going to be 10 by 1, base times height. So the area equals 10 square inches. If you do 2, 2, 2, then we start out with 12 across, 12 inches across. And you fold 2 one way and 2 the other way, we're going to end up with 8 inches. So the area is going to be 2 by 8, base times height, 16 square inches. Okay, so this is better than that if I want to have more area. If we do 3, well, we have 12 total, minus 3 on this side, minus 3, that's 6. So there's going to be a 3 here, correct? So the area is going to be 3 by 3, 9 square inches. Whoa, so we went from 10 to 16, back down to 9. That means that it's getting worse. If we did, wait a minute, that's 3 plus 3 plus 3 is not, that. Yeah, that's wrong. We end up with 12. We start out with 12, take away 3, that means take away 6. Oh, 6 here. 6 times 3, 18. Oh, so that's better. 18 square inches. Okay, sorry that I did my subtraction wrong. What if we put 4 across and 4 up? Because that adds up to 12. See, they have to add up to 12. 1, 10, and 1 add up to 12. 2, 8, and 2 add up to 12. 3, 6, and 6, rather 3, 6, and 3 add up to 12. 4, 4, and 4 add up to 12. But the area is equal to 4 times 4, 16. Okay, this is the one that goes down. So we went from 10 to 16, up to 18, now down to 16. Let's keep doing that one more time at least. What if we did 5? So really, really tall. And then across, we would have to have 2. 5 times 2, the area would be 10 square inches. So we went from 10 to 16 to 18, down to 16, down to 10. So some of us might be thinking, well, that's the way to do it, 3, 6, 3. Well, what if there was a 2.5 or a 2.9 or 3. We don't know for sure. That's the problem. I mean, we can guess and check, but we have to guess and check many other possibilities to be certain. And even then, we may not be even certain that 3 is the best one to do it if we fold 3 on each side of this. So let's set it up. Okay, so pretend we're going to fold a quantity x on each side. So this is going to be x as well. And we start out with 12 inches around. Because remember, we start out with a sheet that we're going to fold up, an amount on each side. So we have x and x. That's how much we're going to fold. How much is this? Well, we start out with 12, take away x, and take away x, so we're taking away 2 x's, and then divide Oh, we don't have to split it up. It isn't like the farmer's case where we have to divide by 3 or 2. It's just what is left over. So there's nothing to divide. This is it. Yep. So it's 12 minus 2x. So 12 minus 2x. That's how much is in here. What is the area? Well, the area is a function of x, and it is the base times the height, 12 minus 2x, height, 12x minus 2x squared, negative 2x squared plus 12x. And that is invariably a parabola opening down because of the negative a. A equals negative 2, b equals 12, c equals 0. When do we find the maximum? Well, negative b over, see, I almost messed that up, 2a. So negative of negative 2, divide that by, wait a minute, boy, I meant to say b, so that's 12, divide by 2 times negative 2, there we go. So the two negatives cancel, 12 divided by 4 equals 3. So sure enough, now we are certain that the maximum, look, this is the maximum. This is a parabola with a vertex. And if the parabola opens down, we have a maximum. The maximum will be precisely and exactly, absolutely, no questions asked. Full stop. It will be when x is 3. So this example, we didn't have to go through all of this. I just wanted to show you how we go about it. When x equals 3, we will obtain the maximum area across this folding, and it will be an area of 18 square inches for sure. So this is 318 when we set it up that way. Now somebody could say, can we set it up so x is the bottom? Sure, you can. And then you will end up with the same answer. Well, not the same parabola because it will be 6, 18. It will be a different parabola. Yeah, it might not be a bad idea to do that. If this was x, then what is each one of those two sides? But anyway, I just checked, and it is with a P. I wanted to do that last, so I didn't take up time. It's a P, optimize. All right, guys, we're going to stop the video here.